Okay,
That's what
great. Great to see you again. So today I'm going to teach you SQL like no one did before. Who knows SQL already? Great, almost everybody. So like for the beginning, you should know SQL is the intergalactic standard for data retrieval. So it is declarative, so you do not specify the way how you get the data. Instead, you say what you want. So you say what you want instead of specifying the way how to get the data. Yeah. So now you can hide after I see you. So you can, if you do not want to attend the lecture anymore, I can't see you when you're trying to escape. But I can't escape anymore. So if there's a fire, you will survive, but not me. Okay, so SQL is declarative, and of course it's supported by almost all data processing platforms. And actually there's every 2 years there's a new standard. So the basic SQL, all the features you know, like joining two tables, they are part of the SQL 92 standard. So basically that's the basic support of SQL. Then in 1999, recursive CTEs and grouping sets were introduced. Who knows about CTEs? Common table expressions. 1, 2, great. So I will teach you how to use CTEs, because in my opinion CTEs are really important. It's nice to have. So there are two different possibilities of saving a certain SQL query. So one is CTE, and what's the other way of saving an SQL query? Yes?
View?
Yes, exactly. So CTEs in views, and it was also new to me, there's a difference for PostgreSQL, and what might be the difference between CTEs and views. Of course you can fuse, yes?
Do CTEs get saved permanently? I don't think so.
You have to speak louder.
Do CTEs get saved permanently like views do? Because I don't think so.
Yeah, that's one difference, that you can reuse views within different queries because they are persisted, whereas CTEs are only for one query. But what's also interesting, that PostgreSQL, for example, does not optimize across CTEs, but does optimize across views. So if you have a view that joins two tables, and you have another query that uses the view, the query optimizer can optimize across all the views, but not when using CTEs. I will come to that later, but it was also a surprise for me. And yeah, so recursive CTEs, and basically why are recursive CTEs so important for SQL? You know what, if a programming language should support everything, how is it called? Yeah, come on, Turing complete, exactly. And to get SQL Turing complete, you need to support recursion. Like if you have the transitive closure, if you can compute the transitive closure. So you are actually Turing complete, because like that you can, how is it called? Like you can implement a while loop. Not just a for loop, where you count numbers from 1 to n, but you can compute a while loop. And that's actually for me very important. So actually I really like the SQL 1992 standard. And also I will come to that later about grouping sets. So you can say, okay, instead of just having only one group by attribute, you can have more and replace those which are not part of the group by statement by null values. I come to that later. Then you have SQL 2003. SQL 2003 introduced window functions. I really like window functions. Actually, it's just syntactic sugar for replacing group by queries. But actually, yeah, it's really nice to have, and maybe I will teach it today or next week. Then, newer SQL standards, 2006, XML support was introduced. Let's see whether we can cover this also in the lecture. Initially, I'm planning to cover XML support for SQL. And yeah, like SQL 2011 supports temporal support. So like tuples are only valid for a certain time period. And the newest SQL standard, I think it's the SQL standard 2023, for example, supports array, exactly like array support. So there are arrays in PostgreSQL, but now there are certain array database systems like Rasterman. He's now in Bremen professor, and he suggested to include array support and graph support. Yeah, like graph queries and array support starts with SQL 2023. But fun fact, actually, there's a huge standard, but actually there's no database system which fulfills the standard. So actually everything is standardized, but actually there's no database system who supports the full standard. And that's why actually PostgreSQL is the best one. So if you use PostgreSQL, that's the database system that supports, that comes to the standard the closest. Okay, yeah. Here at the end, we use PostgreSQL. PostgreSQL. By the way, I have to show you a fun fact. There's the database of databases. Is it? No, it's something else. I wanted. No, sorry. Database of databases. Here it is. Dt-Dbcpu-M. Let's see. And actually, that's the list of all database systems that exist. And here you can type in any database system. For example, the one we are using today, which was created by my professor. Let's see, where's Hyper? Here, for example, Hyper. And then you see the compatibility. And here, most of the database systems are actually Postgres compatible, because PostgreSQL is the database system that supports the standard, most of the standardized SQL queries. By the way, what does SQL stand for? Yeah, structured query language, exactly. And some people also pronounce it SQL. Okay, so that was the first slide about SQL. How can we benchmark database systems? Any idea? Yes. By performance, but actually, what would be a good performance indicator?
How fast can you retrieve data?
How fast can you retrieve data? Exactly, but we need data. And the idea is what kind of data can we use, and for what are database systems normally used?
Optimized SQL.
What kind of data do you mean? CSV?
No, like the model. For actually, what kind of data could you model?
Tabular form. Tabular form.
Sorry?
Tabular form of data.
What else? So of course tabular form. But like, so the idea is data warehousing. So there's a data, so the idea is like Amazon is a data warehouse, and the idea is that we benchmark data on a data warehouse. And basically that's the transaction processing council, and the idea is, okay, this is used for benchmarking database system. And here you see actually a table of orders. So these are there are customers which actually have an order, and the order consists of items, and each item consists of parts, and every item is created by a supplier, and the supplier belongs to a nation. And the idea is, okay, if you want to try out SQL, one possibility, if you do not want to install PostgreSQL on your own laptop, you can use, for example, the HyperDB web interface. And you have, if you have to use some playground, you can use the university schema. It's also there in English. Like here you have the university schema, like it's like a professor giving lectures and students attending lectures. And if you want to benchmark data, you can use the TPCH dataset. And here you can, for example, just enter any query, select star from orders, and then you can, for example, see this big order table. And then if you have a look at how we can join, for example, the order key belongs to the line item key, so we can perform a join on line item where order key is equal to the order key in line item. And then we get the big table which is joined together. Okay, so we will use this data set for the next queries I'm going to present you. Yeah, so like again, the beginning actually internally. So what's also interesting, you can configure the size. So for example, the baseline is factor 1, it's 1 gigabyte of data, and yeah, you can download it. And for benchmarking, and basically what is created is like the schema with create table is given, and then also the data as CSV file is given to load it into a database system. So the next slides will be about, we have the TPCH data, how can we get this data into the database, and for when you're creating the schema, like here, we have to specify the data types, and these are the data types PostgreSQL supports. For example, currently I have one master thesis about benchmarking the use of another floating point number, because like in machine learning, they're using a 2-byte floating point, but with a less precision, but with a higher range. And because like all the modern engines, like the GPUs, and also the newest generation of Intel Xeon processors, they are supporting this kind of data type. And because like in machine learning, it's not about precision, but it's about size, and therefore there's a new floating point number type, which is called TensorFloat, which is actually a 2-byte floating point number, but with a smaller precision. So that's currently what a student of mine benchmarks. So you have fixed precision numbers. For what should this be used? Fixed precision numbers?
Currency.
Exactly. Why don't you use floating point numbers for currencies?
Doesn't make sense, the precision.
Yes, exactly. Because like you always know the number of about the smaller currency, so you know where to place the comma or the point, and therefore you have the fixed precision numbers, and you can use numeric like the scale and the precision, the number of digits after the decimal separator. Internally, fixed precision numbers are just signed integers. Okay, so something else. Fun fact about our about Flex now. So they were using for strings, they're using variable character of fixed size, and this because my name has 10, my prename has 10 characters, and they were using only 8 characters. This Flex now could not did not gave permission for me to create lectures, because like Flex now is totally a mess, and therefore they were using varchars instead of text. So never use varchar, just use text for arbitrary length. Because like varchar, the size of the string is limited. Always use text. Okay, and there are also some other kind of data types, for example bytes, timestamps, and which is really commonly used is date. Okay. You remember the null logic? Maybe we have to. I see I need some. So who knows null values? 1, 2, 3. Who doesn't know about null values? Okay. So let's just do a short recap about null values. So actually, if you do not specify the data somewhere, you can also do it just using PostgreSQL. So, okay. So if we create a table, what kind of table? How do we name the table? For you, for example. And so what do we insert? We can insert something like an integer, like the primary key. And then we can specify some others, like another integer. Okay. So we have created a table. If we now select anything, select star from the table, we have now entry. Okay, so now we can insert any data. Insert into for you values. And then we can insert, for example, 1, 2. And then if we query it again, okay. And if we now enter any other value without specifying the second attribute, then we are using null. So if you do not see anything, we are using null. And null just means we do not know anything about it. And actually, null values make the life hard, because you have to consider null values for every logic. Like, if you have for example, for AND, if you have Boolean values, like you have true and false, you have true and false. So true and true, what's the result? Of course, true and false, it's false. True and false, false, and false and false, also false. And now you also have to consider null values. And if it's null, we cannot assume anything. So actually, if we have true and null, we do not know about the data actually. So true and null also evaluates to null. So if we have false, as soon as there's one false, of course, it's always false, because as soon as one part is false, the whole statement will be false. And yeah, and actually that's why we do not have a binary logic, we have a ternary logic with null values always. And here again, if we have null and true, we do not know, we have null. And we have null and false. As soon as one part is false, we have false. At null and null, of course, means null. So this is actually ternary logic with AND. We can also do the same for OR. So we have true and false, we have true and false, and then true and true or true is of course true, and as soon as one part is true, the whole statement is true when we have an OR connection. Again, true and false is true again, and false is of course false. Okay, and now let's introduce null values. Null values. True and null. True or not and, true or null. What's the result? Who says true? Great. Who says false? Who says null? So of course, as soon as one part is true, then the whole statement with an OR is true. Therefore, at least as soon as one part is true, everything is true. If it's false and null, false or null, we do not know. It might be true, and therefore it's null. Then again, we have to do the opposite. Also, if there's one null entry, null and true is true, null and null and false is null, and of course, two nulls are null. So we can also try it out. We have to create another table. Create table Boolean with a what should it be? A Boolean. Insert into Boolean values. We can true, false, but actually we need an identifier. Let's do it without. So insert into Boolean values true, false, and null. So where's the true does not exist? Okay, interesting. True. Do I have to specify it directly? Interesting. Select star from booleans. Okay, so we have all the entries. Now let's perform a cross product. So we have a cross product, and now what we can do is we can B1 A, and then not sure whether it's AND or whether we have to use the ampersand. Yes, and here we can see true and true is true, true and false is false, true and null is null, and there false and true is false, false, false is false, and false and null is false. And if there's only one true, it's false. If there's at least one false, it's false, and two nulls is null. We can also do the same for OR. And here we can see as soon as there's one true, one attribute true, the whole result is true. Yeah, so you have to remember always when using SQL, you have a ternary logic considering also null values. How can you avoid that null values will be part of a table? Yes? Exactly. So if you want to create a schema without null values, you can specify it as part of the attribute. So here behind Boolean, you can say not null. And then you have created, you cannot insert a null value into this table anymore. So if we now want to enter null, failing, because like we have the not null constraint. Okay, by the way, what's also really interesting, and it's a bit of brain fuck, if you create, so what was the other table we called it? Value. No, not values, it was for you. So select star from for you. Okay, what's interesting is if you have aggregate functions, like if you have the average, then the null values simply do not count. So null values are ignored. And then I think there's a difference if you have to count it. For example, if you use it for count, you see then null values are ignored. Because if you count so you can do a difference between count star and count only the value itself. Like here, null values are not part of count, but actually for all the other aggregate functions like average and sum, they are just ignored. So it's a fun fact that actually null values for the aggregate functions are not considered. Okay, so now you know also about nulls and how the ternary logic works like. And if you want to know about all the data types that are supported in PostgreSQL, there's a list in the documentation. For example, for me, arrays are really of importance. I want to use arrays for everything, like can we use arrays for creating matrices as used for machine learning. That's also one of my research interests. Okay, so now we have the table, we have the data types, and now we need the data. So basically when you execute the TPCH generator, another thing, TPCH, actually Transaction Processing Council, and they have A, B, C, D, E, F, G, H, so actually 8 kinds of benchmark, and that's why we're using TPCH, because the complexity grows with every benchmark, and TPCH is like the de facto standard for analytical queries, and there's also one for wide-hairy queries. That's the TPC-DS benchmark. Okay, so if you run the TPCH benchmark, you actually get a CSV file, and so actually line item CSV, it's actually a CSV file, but instead of using commas, it's separated by pipes. So that's the file how it looks like. And then you can create, okay, so this is the database we create. PostgreSQL, we have to create a database before. And then the idea is we can load the CSV file into the table. So we have to create a table like before. So that's the table. And now we import the CSV file. We have to specify the delimiter. And then we get an error message because like all the files have to be, should end by, what should it end like? Yeah, like every line should end by a pipe, and therefore we have to add a pipe at the end, and then we can copy it. So it's a pitfall when you copy data as CSV into database system, the database system expects a delimiter at the end. So that's what is shown here. So, by the way, these are basic Unix commands. I'm not sure whether I should teach Unix commands. So who knows basics about Unix commands? 1, 2, 3. So actually 4. I have some slides about Unix commands, how you can use SED. So SED is just regex. So here you say substitute, and then inside you say what to substitute. So this means, okay, at the end I want to substitute the pipe at the end by nothing. So actually the CSV file is using a pipe, but sorry, others, as I explained before, PostgreSQL does not want to have the delimiter at the end. So here we substitute away the delimiter, replace it by nothing, and we do this in place inside of the file. So SED is really powerful. It's Turing complete, and yeah, maybe I'm going to teach you some basics, and with head just means you get the first line. Okay, and then that's how you copy the CSV-like data into a database system. Okay, so that's a basic, oh, not a basic SQL query, that's a SQL query with everything. So we have basically here 3 tables that we join by the key. So we join it here by the different keys. Questions? Question?
This is everything. Did I understand it correctly?
No, that's not everything
Okay.
SQL knows, but it's all the basic clauses. Because like you have the select clause, you have the from clause, you have the where clause, you have a group by clause, you have an order by clause, and you have a limit clause. And yeah, it's like you have 2 joins, because you have to join customers with orders. So we join customers with orders. You have to join orders with line item by the key, and then you want to get only those orders which are ordered before 15 March 1995, and those which have been shipped to the customer after that date. So not on the same date. And then you want to get just the aggregate. So you aggregate by the order key, the order date, and the ship priority, because you want to know the whole price which has been, so you want just to get the amount of money which has been ordered before that date and shipped afterwards. So we can also copy that and execute this here in SQL, and here you can say see the revenue, and that's by each order key. So that's actually you aggregated by order and get the money, how much was sold, and by order date. Okay, and now it's up to us to create some other SQL queries. How many items were shipped by German suppliers in 1995? So actually I've created those queries beforehand. No? I think it should be this one. Or was it this one? Yeah. So how many items were shipped by German suppliers? So the idea is, okay, we only want to have the suppliers which are from Germany. So the first thing is what we do is we say, okay, the nation, we need the nation table, and the suppliers should be from Germany. Okay, and then we have the suppliers, of course. We have to join the supplier with the nation key. So if you have a look at nations, it's actually just the table of all the nations that exist. So you have a nation key and you have the name, and basically each supplier there's the nation key. So that's actually the manufacturer who gives you the product, and every supplier has a nation key. So the first thing what we do is like we join it on nation and get those where the nation key, where the nation is Germany. So here, no, it's the wrong one. Here the nation is, where is it? Name nation.name. So nation.name is Germany. Okay, I made a mistake. So I forgot the second to join. So supplier dot nation key should be equal to nation dot this TPCH schema. There's always in the TPCH schema, every key has one character for identifying the table actually. So we do not have to specify the table beforehand. So we have nation.nation key and the nation name should be Germany. Is it really nation name? It is. But it does not work. Why doesn't it?
It's just a name. Yeah. It's not mentioned that.
Ah, thanks. That's it. N underscore. Because like we always need the character beforehand. That's why it is. So now we have attached to each supplier the name of the nation name. So here's the nation key, and here we have added the name. Okay, so this was the first part. And then we have to count the number of items. So let's have a look. So we have the supplier, and how can we get the items? We can get the items only our part supplier, I guess. Oh, I have to cheat, sorry. We have nation line item. Line item has a supplier key. Okay, so line item has a supplier key. Okay, it's basically the same. The supplier key here is the same like for supplier. Okay, and then we can use this for the join on supplier. So basically we can get here the big query, but we only want to know the sum of how much was sent by Germany, and then we get just the sum. Okay, if we want to know how many items were shipped aggregated by each nation, how can we make this? No.
Count
Yeah, sure, with count. But currently we sum it up. No, that's not count. We can count the number, but so the idea is I want to get rid of this and nation name is Germany. Yes, group by. Who said it? Thanks. Group by what? Yeah, exactly. Does it work now? Yes, it will work, I guess. But we have also to specify it as part of the select clause. So here we see it aggregated by each nation. What's also important, every attribute that is part of the select clause and that is not part of any aggregate function must also be part of the group by clause. For example, if you want to add some others, for example, what's part of it? Not the quantity, you ask for getting the number. Of course, we can also add this here as count star. Anything else? Yeah. Okay, so first query, we have another query. What are the names and account balances of the 10 customers from Europe in the furniture market segment who have the highest account balance?
Having,
Hmm?
yes, we have to use
Having.
after older one.
Mm-mm.
So we can put clause in both dimension.
So actually, how can you get the best one? So like actually, I don't like the query how it is proposed as part of the slides. How can you get the best one?
Using max period. If you want the highest one.
We can. I think I did it in my seminar last year. Maybe I still have the queries. I guess so. Seminar. It was last year. Let's have a look whether it is still here. No, it isn't. No, it isn't anymore part of it. So let's select. Let's create a CTE. So if you want to create tuples without having write permission, you have to use CTEs. And therefore you can get, for example, the score of someone. And you can say, okay, you have the name and you have the points. And then you have to fill it with data. For example, you have me and I have a low score, only 1 point. Then let's use the most basic ones. Alice, who has more scores. And let's use another one, Bob, who's among us both. Okay, and so that's by the way, that's a CTE. Just with, as, and then the values. And you can query this now, like a normal table. So here we go and we get our table. And now if you want to get the best one, you said with one possibility would be with aggregate function. So where the points are equal to the best one, so we need a correlated subquery. Select star from score, and now you say you want to use an aggregate function, points from score. Hmm?
Shouldn't we use write down? Okay.
What do you want to use?
No, fine.
What?
I was saying about group by.
Group by, no. So actually when you so it's always so if you have a query plan, so basically if you have using an aggregate function, it's always an aggregation. You have to use group by if you want to have, for example, if you have multiple disciplines. For example, if you have disciplines like I am good at nothing, I'm sorry, but maybe it's say sailing. So we have the discipline now added. And Bob is not good in sailing, he's good at surfing. Okay. This still should work. Yes, of course. And now we can say, okay, actually it's nonsense to have group by query here, but what we can do is we can create another CTE. We can create another CTE as the best ones, and basically the best ones, it's the best one by discipline. Okay, and then we we have just a table of the best one by discipline. Looks good, doesn't it? Unexpected select. Why is it unexpected? Select max points from score group by discipline. Actually, it should work.
I think you're missing the S after this one.
Yes, that's it. Thanks. So here you get the best one by discipline, and then it's always good to have the grouping key also as part of the select clause. Now you see the best of the points here as maximum, and then we can say, okay, the best ones by we want the names, and how do we get the names? By joining it here from best ones and scores, and then we need a join where the scores dot name is equal to the best ones, not the names, so the discipline, of course. Is equal to the best ones dot discipline.
Scores kind of this aspect of it.
Yeah.
So,
Okay. Why am I part of it? So I made a mistake. So I shouldn't be part of it. Score best ones, because of course I'm joining it. And score dot points should be equal to the best ones dot points. And now I'm only getting those which are the best. And here I get only those who are the best in their discipline. I can also add the discipline here. Here I get also the discipline. Okay, so that is an example how we can use group by as part of getting the best one. But actually, that wasn't the point. So I wanted to show you how to use, how can we get the best one without using an aggregate function. That's actually what I wanted to show you. So again, we say, okay, currently we did it with an aggregate function. Where so this was the variant with an aggregate function. And how can we eliminate the aggregate function? Yes?
we will make it orderable at first, then limit.
And that's one possibility, but actually that's a bad possibility. And that's also the point why I wanted to show you that's not the best approach, how the slide actually proposes to get the best one.
Rank
Hmm?
function? Rank function? Rank.
That's a window function, isn't it? So currently we still do not know window functions. Currently we are still in the world of SQL 92. We do not know about window functions. So the goal is to get the best one without aggregates and without anything else that does so without aggregate function and only those statements that exist in SQL 92. So yeah, I will show you how it works with limit. And basically what you propose is you want to order it by the points, descending, and say we want only the best one. And we should get Alice. So obviously it works. But now what about if we have two best ones? So now Alice and Bob should be part of the result. Are they part of the result? No, they are not. So actually, limit does not give us a top query. So actually the top query means we only get the top best, and it's, for example, top K. Like if you, like in Olympic Games, like you get a gold medal if there's no one better than you. So if there are two which are as good as there's another one who is as good as you, he also gets the gold medal. It was like, for example, in the last Olympic Games, I think it was in the kind of jumping with I don't know the word. In Germany it's Stabhochsprung, and the English one is, so there was the case there were two the best ones, and basically both got, so it's pole vault, and both get the gold medal, and that's actually a top K medal, a top K query. You get a silver medal if there's only one who's better than you. So so let's Olympic Games. It was when was the last Olympic Games? I think last year. And gold medal 2, and let's see whether there's the case.
It was the normal high jump.
It was the normal height.
The last Olympics, not the last one. In the Japan Olympics was the normal high
Really?
jump.
So it was here and normal height jump. Yeah. And actually, like, if you have 2 gold medals, how many silver medals do you have? No one. Because, like, for the silver medal, there must be only one who's better than you. And there were two with gold medals, so there's no one for silver. And actually, this logic is the one we have to use. Yeah, here there were actually 2 gold medals. Yeah. But then if there's 2 gold medals, there shouldn't be any silver medal. And now the question is, how can we model this in SQL? So the question now is, Alice and Bob should both get a gold medal. But using the limit clause, we only get one. So with Max, it's actually correct. Here, we should get both, Alice and Bob, so it's fine. So actually with aggregate functions, it works. And now the question is, how can we get this without window function and without aggregate function? So when are you yes?
I don't know if it already existed, but maybe it exists. And we can use not exist and then check if there's any value that's higher for each row.
Exactly. So you get the gold medal if there's no one, no one exists who's better than you. And that's what we can type in now in SQL. So here we can say, okay, select only those where not exists anyone who's better. Where not exists anyone is better. And here from score S2, and now S2, no one should exist where S2 dot points, so who has more points than you. And then we see Bob and Alice. So that's the way how you get the best. Without aggregate function and without limit. So if you're ever asked about getting the best one, about getting the top ones, you should avoid limit, but instead use exists and not use not exists. So I think in the next week, because I also have to prepare it myself, I will show you how also get the silver medal and so on. I showed it in my seminar, I think it was last semester. Was it in the winter term or was it the term before? I thought it was last semester, yeah. So you can also, you get the silver medal if there's only one who's better than you, and you can also model this in SQL with not exists. Okay, so why am I talking about top queries? Because like here, we should get the names and account balances of the 10 customers from Europe in the furniture market segment who have the highest account balances. And basically the query which is proposed here actually uses limit, and therefore I'm not that happy with it. Yeah, so here it is. We have all those from Europe, and we only want the best ones, and here we're using limit clause. And actually this only works if the number 11 is not the same as good as the number 10. So actually it's a bit of cheating, because you should not use limit for top K queries. Okay, so actually I've already shown you that you can use subqueries inside of SQL. And for example, here you can add for every name the number of all regions. Doesn't make sense, but you can do it. So it's a subquery. You can also do it here, like here. So you have one table and then you create another table, and actually that's the table with all the content which is part of from the region Europe. And then you do a join, and then you want only those regions with at least one customer. So there exists an entry in customer in this same nation. So this actually is a correlated subquery. And the idea now is, how can we get rid of correlated subqueries? I'm not sure if there I think it's the first I've created also another example on that. Let's have a look. No, that's it. It isn't.
Isn't this type of work a task for the DBMS?
It should, yeah. But not all DBMS are so clever. So you have to discover that. So there are some basic, like trivial things, what you can do, like you can put this out. Okay, here that actually doesn't matter here, because like the worst cases are those which are part of the select clause and which are part of the, let's type it in and let's do it. Okay, what happens? Here we have the query, and now we can see the query plan, and we can see the unoptimized plan. And actually there should be a cross product, so we already do some optimizations. So the first thing what we can do is, actually we can get this subquery away. We have region and we only need region name here. So we can get rid of the first subquery here. Okay. What else can we do? Actually, this shouldn't be part of the select clause. We can just do this here. Because actually, let's do the query again. It's always the same number. Yes, it is. Of course it is. So what we can do is this can be part of the from clause actually. This can be part of the from clause here, and we need a name for it as count, and yeah, just count. And here, okay. And actually this should be the same query now. Unexpected comma. Where's the comma? Here, of course, because we need an AND. And now we have the same query but decorrelated. Exactly. So we have the same query like before. Should have. And do the proof. One, two, three, four, five. Yeah. Okay. And the idea is that we decorrelate manually those queries. And a query is correlated if it refers to tuple from outer queries. So like before, we do not have any references. Like here, we have subqueries, but actually the subqueries, they are not correlated because they do not refer to something outside. So here, it's just select count from region, but we do not make use of the result here, for example. So actually that's not a correlated subquery. A correlated subquery is correlated if it refers to tuples from outside the query. For example, here we have the extended price, and we want to match only those which have the same order key here. So here we have all the line items where the extended price is equal to the minimum of the same order here with the same order key. And the pitfall is actually we have to execute this query here for every tuple. So everything which is part of the select and the where clause has to be evaluated for each tuple. And therefore the idea is to avoid correlated subqueries. So for example here, we want to get this part out of the where clause. And we can do this by putting it into the from clause. So here we say, okay, we just group by every order key, so we only compute it once, and group it by every order key. And then we can say, okay, we compared the order key here, and compared whether the extended price here is equal to the one we have, to the minimum we have computed before. And that's one idea, because like you see, this needs some kind of intellectual work. Like you have to transform this correlated query into an aggregate beforehand. And we can try it out whether the query optimizer is able to do this. So this query, let's type it in. And we can see the query plan. So the unoptimized plan. And now let's, where is it? Now let's have the other query. Let's show the query plan here. Okay, so actually in this case the database system is able to optimize it, yes. So good database systems are able to optimize it, but not every database system is able to do it. We also can compare the unoptimized plan and actually it was the unnesting here. Like we have a explicit phase in optimization which does the unnestings, but beforehand we had a different query here. Okay. Here's another challenge, decorrelate the following query. So we have all the customers of the market segment automobile, and the balance should be higher than the average balance of all the customers in the same market segment. Any ideas?
But then in the from clause.
Mm-hmm. But what should we put into the from clause? So actually what we should do is, if you compare to beforehand, what we did was, instead of comparing the order key for every item, we created an aggregation beforehand by the order key. And then we must do the same for market segment. So, where is it here? Let's try it out. So here, let's query it. And the idea is, okay, instead we should create a subquery here. Basically, we can also do it with a with clause. And now we do it, we group by each market segment. So we need a group by, and actually that's it. So if now our subquery we can use, we have to use our subquery, and then we have to say, okay, it should be higher than the one we queried before, so it should be higher than the average. We have to name it maybe. So we have to create first a join, so this market segment must be the same. So here the sub market segment should be equal to our market segment. And okay. So it must be an OR clause, and the account balance should be higher than the average. And now we should have the same result. Yes. Let's have a look whether that's what also the proposed solution was, or was it different? Yes, exactly. That's the trick. You have always to aggregate it beforehand by the market segment, so by the value which you're comparing to. So exactly how I did it. First, creating group it by the value, and then you can recompute all the values you need. So actually, I myself am not the biggest fan of using the TPCH queries for teaching. So normally, maybe also for the next and for the window functions, I have prepared the queries on other data sets, like for the university schema. But for decorrelation, I'm using the queries on the TPCH data set. I'm not the biggest fan of the TPCH data set. So for the next queries, I'm using some smaller data sets. Yes. Okay. So much about decorrelation, and now about other operations. So set operations: union, except, intersect. What does union does?
It joins two different.
No.
Then one of it.
Hmm?
It becomes all. It becomes all.
Union does all.
If we union two tables, it becomes all the unique values of two tables.
Without any repetition.
So of course, because it removes duplicates. So union, by the way, what's the precondition for set operations? They need to have the same attributes, yes. And basically what we do is combining two tables. Like having two tables with AS So let's query both. Here, union is actually without duplicates the combination of both. I still have a mistake in my query. Why? It should not work. Oh, it does work. Okay. I did not. You have to use the same names. Interesting. Only the same attributes. Interesting. Okay. It works. So union just gives us the unification of both without duplicates. How can we what's the opposite of using duplicates? How can we also get union all, exactly. So if you enter all behind, it's without duplicates. Okay. So what else? Intersect gets only those which are part of both. So it's only two. And except is just the minus. So just as gives us those which are part of the first but not of the second table. So it should be only one. Yeah. Okay, so if you want to also have with duplicates, you can just add all. Yeah. And some other, it's like case statements. You can also use like if statements. So if there's if you want to name it, you can just use case when statements. Okay, let's go back to our example with the null values. How can we use? How can we substitute null values? So we had the table for u, and we want to substitute null values. How can we do it? So tell me how. So when case when b is null, exactly. So we have to substitute it by 0, I would suppose. Is null, then 0, else b. I guess so, yes. And do not forget the end. So here we had one null value before, it's now 0. Is there a shorter form for that? It's nice to have, and you need it frequently. guess it was with an E at the end, yeah. So it's like this one, instead of checking for null, you can just use coalesce. It's the same result. Just nice to have if you want to substitute null values. So what also might be interesting is casts. For example, we want if you want to compute the average by hand, for example. Yeah, so let's have again a look into the query. And if you want to say, okay, or you want to divide A through B, how can you do it?
Dividing more sense.
Hmm?
Dividing more sense.
Divide it?
You said divide.
Divide, yeah. You just want to say, okay, we have two values, and you say you want, okay, A through B. Division. Does this work?
If we use cast, then it will work.
Hmm?
The wrong data type.
It's the wrong data type, exactly. What do you,
Casting to int.
not to int, we have already int, but to something else.
Float.
For example. Yeah, that's one possibility. If you do not cast it, because like you get take the original data type, you have integer and you would have 0 because you would cast it to the, you have to do integer division. By the way, if you want to avoid cast, so there are two other possibilities of getting floats. The first one, but which is just syntactic sugar. Instead of casting, you can say, okay, just float, and this works. And there's also another alternative. You have to add a statement using a float. So if you just multiply it by a float, you take the most compatible one, and in this case integer float. So you cast the whole statement to float, and actually this should also work. Okay, because we have to compute it first, and now it also works. But I think now it's another data type. It's not float. I think it's numeric. Is it? No, it's, we can't see it. Why can't we see it? So I think it should be numeric now. Okay, I don't know how I can see it, the data type. Okay. So now you have seen casts, generate series. So it's also useful if you want to get a random series. So you can say, okay, generate series. You can get just a series of numbers. You can also specify a step, only go +2, for example, and also there's random if you want to get some random numbers. For example, if you want to create 10 random numbers, for example, rolling a dice, you can say, okay, random is integer +1. Okay. Strings. We also have strings in database system, so you can do the concatenation with the double pipe operator. You can use string matching. So this is for arbitrary length data. You can also substitute only one string, one character. How can you do that? Instead, so let's do the example here. What's the result of this query? Mm-mm.
Just like it.
What's the output of this term? What kind of data type is it? Data type, yes. Boolean, exactly. So what's the result? True, of course. So we should have true here. And so the percentage sign means we can replace it by arbitrary character. And if we only want to have one character, for example, if you want to say, okay, ABC foo, instead there's the question mark. It's only one character for replacing. This should be also true. No, it's false. Why is it false? Oh, sorry. Okay, sorry for that. Okay, we can also do regular expression string matching with this one, and we have also extract. Just say, okay, we just want to have, we extract a substring from that, so we only want starting from position 3, 1, 2, 3. We always start by 1 in SQL. We only want to have CF. So if we want to execute this statement, we also only should get CF here, as I said. Okay, sampling, which is also interesting. You behind the table, you can add. Okay, we only want to have a certain number of of tuples. So PostgreSQL also supports sampling. So you have different kind. Reservoir sampling, which gives you an exact amount. So if you instead of Bernoulli, you can enter reservoir and the number, you get the exact number. With Bernoulli sampling, you get the 5%. Yeah. And by the way, using limit is actually the specification SQL of limit is not the best 10, it's just arbitrary 10. So by the default SQL standard with limit, it's actually a way of doing sampling. Okay, we can do it, compute the average total price using sample of 1% of all orders. Let's have a look whether I've saved it. I guess so. No, I didn't. Okay. So, total price of orders, select star from orders. Where's the total price? Oh, total price. Average of total price, and then what should we do? The average using a sample of 1%, and then we should enter Bernoulli, but I'm not sure whether the database system supports it. Do we? Let's have a look. Okay, it is not supported, but actually that should be the query. But I guess in the other database system, Umbra, it should be supported. Oh, sorry. It's another research prototype of a database system, and this one should support Bernoulli sampling. Oh, it does not, but reservoir sampling is supported. Yeah, so reservoir sampling is supported. Okay, I'm sorry for showing you a database system that does not support sampling. Okay, so we still have 10 minutes. And the 10 minutes can be used for a short introduction of use and common table expressions. So you have already seen common table expressions. It always starts with the with. Then you have the name, and then we have between the parentheses you can enter any SQL query. And then you can use it as like every other table you can use. And the other possibility is using views. if you have write access to a database system, and basically views and CTEs can be used as normal regular tables. And the difference is, for example, in PostgreSQL, with is an optimization breaker, views are not. And by the use views and CTEs, code reuse, abstraction, readability. And if you need a table a view more than once, you can create a view. If you only need it to structure one SQL query, you should use CTEs. And the idea is you can use CTEs for the recursion. And the idea is, okay, so as I said, it's Turing complete, and you start always with recursive. This means you have a recursive CTE, and then it has two parts. The first one is the non-recursive term, so the base case, and then you have the recursive case. So for example here, that's just a for loop that computes you all numbers between 1 and 5. So we can try it out. So here 1 to 5, 1 to 4, 1 to 5. So it always uses the step before, plus 1, and we do this as soon as our previous one was less than 5, so we stop for the 6th iteration. So that's how you can do an iteration in SQL. So here's another example. For example, if you want to get all the descendants, like, and the idea is, okay, we have a table which only has one ancestor. Like reptile is an animal, a snake is a reptile, we have mammals, mammal is an animal, a tiger is a mammal. So actually, where is it created? So so we have an idea, and here we see a mammal is an animal, using parent and null values. And now we want to get to recurse the transitive closure. So you want also that a green sea turtle is actually an animal. And the idea is, okay, we can use this using recursion. So let's try it out. So here we have our base table. Select star from animals. And magic. So here we see actually the table. Every animal has an ID, and this ID can be used as foreign key here for the parent. So in the first step, what we want to do is, okay, we want to join it. So we have the base case. So we have animals base and animals 2. So where the animals 1 ID, so actually we have the parent one and the child, and basically the parent ID should be equal to the ID of the child. Okay, so here, so I made a mistake. Where is it? Of course, I joined everything. So what I want to have is the parent ID. So the parent ID should be the parent of the child, obviously. Okay. And here, but now we should have done the correct join. Here we see that a reptile is an animal. A mammal is an animal, a tiger is a mammal, and so on. So this is actually our base case. So okay, we take the outer one. So take the child ID and the parent. Guess like this. Yeah. So this is now our base case. Yes. So we have our base case, and then we can do our recursive case. So we say, okay, instead of now using the animals, we should use our recursive step here. And now we have all the recursive ones. Unknown column child.parent. Okay, I've done a mistake, otherwise it shouldn't take that long. So basically how it should work is like we have the base case is just parent and child ID from animals. This should be the base case. Okay, and then we should join it on one side. We have always the ID and the child. ID, parent, child. No, otherwise, child, parent. Let's do it like this. So here we have also ID, parent. Okay, and now we have the recursive case. We have the parent, animals parent, and we have the recursive child. And now the inner ones should be equal. So we, from the recursive ones, we join it on one side. So animals dot parent should be equal to rec dot child, and then we take the one on the left and the right hand side. So we need animals.child and rec.parent. Okay, and this should now work. Okay, so where's the animal? It's called ID, right? Animals. Here, it's called ID. And now we see the transitive, we have computed the transitive closure. And now what we can do is, we can say, we can join the names, animals 1 and animals 2. And don't forget the where clause. So rec dot, so it's confusing that I'm using child and not ID. So rec.id should be equal to a1.id, and rec.parent should be equal to a2.id, and here we can say, okay, a1.name, a2.name, and now we should have computed that the mammal is an animal, the giraffe is a mammal, but also the tiger is an animal. Yeah. And now we want to know all the descendants of the turtle. So, and where the name is equal to green sea turtle, and here we can see that the green sea turtle is a turtle, but it's also a reptile and an animal. Yeah. So that's an example how you can use recursion to compute a transitive closure. And it's always like you have the base case, and then you have to join the recursive case here on one side. So you have the ID and parent, and now the parent must be equal to one ID, so the inner ones are joined, and the outer ones are used for the recursion, and that's how you can get the transitive closure. Exactly. Questions? If it's not the case, we make a short break. When should we continue? At 6 o'clock?
Yeah.
So,
Sounds good.
see you again at 6 o'clock.